Scott, Brett, and I are very excited to have you today. There are some quick rules that I want to discuss with folks who have tuned into this webinar. You should see on your screen, your Zoom interface, that there is a question and answer or Q&A box that pops up when you click that button. I'd encourage everyone to click it and have it open and dialogue with these panelists as we talk through this site that we have planned to discuss today. So please ask questions along the way. We appreciate your questions. Some folks are probably wondering, where's Gorm? Gorm is usually the host of these events. You're stuck with the backup squad here today. Myself, I will be hosting. Gorm, unfortunately, is under the weather today, so I am filling some big shoes. Please be patient with me as I take on those responsibilities. So, quick introduction of this site in Indianapolis, Indiana. Wilcox and their client implemented a combined remedies strategy working towards site closure. The actual source is at the very top of the screen up here. You're seeing a data set from a couple years ago, that shows a very long down gradient plume. And then the data on the right-hand side shows what it looks like just now, essentially. So the source is trichloroethene, and we are going to be talking with Scott and Brett about how we together as a team implemented source control in the soil located at the site, and then down gradient passive reactive barrier walls that Brett and his team installed. So combining strategies is nothing new. We've heard about this various different lectures from Mr. Cummings, Jim Cummings here. He's been talking about this for years, probably decades, right, Jim? We appreciate, his advocacy over the years for these smarter remedies, and this is just one of many combined strategies that have been implemented with thermal in the source. So we're excited to be talking about that today. So Scott, I'd like for you to introduce the conceptual site model a bit more and talk about, what were the site conditions? How did you end up making decisions on, where to implement thermal versus the injection strategies that were implemented?
Thanks, Lauren. Hi, I'm Scott. It was a fairly simple CSM we had going here. Former industrial practices, leak spills, whatever, resulted in a fairly significant mass of TCE relates to the subsurface. As you can see by the conceptual site model, the upper about 10 or so feet was a lot of fill material, urbanite we call it on here. It tends to be very clayish, silty, and then we hit a natural clay layer, and just had a lot of, it was pretty much free product bound up in the soil. And as that continued to leach downward, hitting the very prolific and porous and permeable sand and gravel layers, and started following the typical groundwater path, which near the river, as you can kind of see by the shape of the plume, was generally towards the south. So it had been leaching for decades, which is what extended to that the long, typical, I guess, textbook cigar shaped dissolved tornadic groundwater plume. So we looked at it from 2 points. We knew we had a source here that we needed to treat, otherwise it was just going to continue adding fuel to the fire. And then we wanted to treat the groundwater down gradient to prevent offsite exposure to the property owners, to the ecology of the river. Knowing that we couldn't treat the entire plume thermally, at least not financially, would have been difficult. So we kind of looked at how can we hit both, knowing injections weren't going to work well in the source area because of the tight nature of the material, or like the soil. We looked at, doing thermal to basically cut the head off the dragon, and the injectables by Progenesis to kind of just bisect the body in parts. That's kind of as it was a little more in depth of a process figuring this out on how to do it, but that's what we came up with. The clients loved it. They said, "Wonderful, we want this problem taken care of." And this is what we came up with. And then I approached TRS and said, "Need a plan?" Called Brett and said, "Brett, need a plan. Let's put our heads together."
I love it. A little bit more about the source area, just zooming into the north side of the site and actually taking a look from within that manufacturing building, right? This is just a small portion of the building that we're looking at here.
Correct.
Yeah. Would you mind explaining a bit more about what we're looking at and how you ended up drawing the line for essentially the area that we were going to target for thermal?
Absolutely. Well, you can tell again, it's a typical Chembox analytical map. The areas in red are where we had the most elevated hits. This is showing TCE in parts per billion. We kind of translate that to, the way we look at things, at least in Indiana. The highest one in that 4 to 6 zone ends up being 1,600 parts per million. Based on the calculations we did with TRS, with the amount of TCE bound in the soil, was pretty obvious to us that there was free product still bound up in there. So we knew we couldn't, again, treat unsaturated soil with free product with injections. Excavation, while there's some circumstances would be possible, was ruled out for the site for various reasons. So thermal became the best option that we had, and we looked at where we had the highest hits, or the most elevated concentration, kind of focused on that being the source area that we needed to treat thermal.
Yeah, these circles, I mean, a lot of these concentrations are indicative of DNAPL, right? So, unfortunately, with injection strategies and DNAPL present in that tight, silty clay subsurface, it's going to be a pretty tough strategy. You needed a bit more, a bigger hammer in this small volume of soil.
Yeah, it wasn't large. It ended up being, I want to say, approximately like 1,700 cubic yards. Oh, there you go, 17.
Yeah.
It was approximately a 40 by 40 foot area, so it wasn't large, but just the amount of TCE that had been lost to the subsurface over the years was substantial, which again led to the DNAPL in the unsaturated soil and that long, again, just cigar-shaped plume in the groundwater.
Yeah, so you mentioned it's not a very large area, Scott. It was, I remember visiting the site back in the day. It felt big at the time, but then, once you were able to take down all the interior walls inside of the building, you realized how small it ended up being. Before those walls came down, we were in and out of different rooms, so it felt very large. But we only ended up installing 11 electrodes for this site. So very small condensed source material that you were dealing with. It took about 4.5 months of heating, right, in the end, and just about 500,000 kilowatt hours to get us across the finish line. That was a guaranteed soil remediation. So I know those soil goals were really important to your clients, and it was actually built into our contract in the end.
Without a doubt, yeah, that was one of the big selling points to the stakeholders, because again, this is a problem that had been a thorn in their side for years, and they just said, "What can you do to make it go away?" and promise us. So the contract we had with TRS was for a 99% reduction in TCE in soil. So we were going from 1,600 down to 16, and in our regulatory environment, that was actually below IDEM standards. Client didn't care. They said, wonderful, make it that clean. We don't want rebound either. So we made the site cleaner than we needed to, but it resulted in a very happy client.
Yeah. So from TRS's perspective, we used one of our smaller power control units. You could see that unit here in the center of the screen in this layout. There was field transformers deployed to this site. So we did step down voltages out to the field just as a optimization measure. We can vary various different voltages to the subsurface. And that's exactly what we ended up doing with these electrodes. So big hint there, the thermal technology that was deployed at this site was electrical resistance heating for the subsurface. We did, use the building itself as cover for this equipment. So what you're looking at, this is the exterior of the building, and then this is the wall, and everything inside here ended up being placed inside the building. So you've got a vapor recovery blower.
Pop up for that was the building removed or existing? No, the building remained. We took down some of the walls on the inside, which actually was wonderful because we were building this system all throughout the fall and into the cold winter months, November, December, January, and in a building to work in was, I gotta say, it was nice.
It was very nice. Yes, nice warm subsurface too that provided some radiant heating, right, for all the workers on site.
Quite a bit, and also gave us, because of the size of the building, gave us a wonderful place to store all of the products from Regenesis to keep them out of the freezing and keep them protected from, people who want blue stuff.
Yeah. So a little bit more details about the subsurface design here. You're looking at the electrode that was typical for this site. So all 11 electrodes looked like this. Fairly large diameter borehole, in 12-inch diameter, all the way down to the very bottom of the target treatment interval, and actually beyond that by a few feet, just to overcome known heat losses that we plan for at the very bottom of the treatment interval. So you can see some of the geology that Scott, you were describing earlier. We ended up, encountering a layer of gravelly sand right above the clay that we expected. And we actually worked with Regenesis, and some of the data from the flux tracers gave us some information that we needed to determine, should we deploy hydraulic management, or is this zone slow moving enough that it wouldn't adversely impact the heat that we're generating in this treatment volume. So a little bit more on that data set later by Brett, but that was really helpful and some good synergy amongst team members.
Yep. Another point with that also, Lauren, on the cross section, we went a couple extra feet into that clay aquitard, which we found to be ubiquitous throughout the project area. We tagged it with a geoprobe. We wanted to make sure we knew where our treatment zone was going to be for both the thermal and for the injection. Biggest reason to go, several feet into it in the source area. Again, the Dean apple, that much TCE. We didn't want to deal with any back diffusion or resorbing into the groundwater once the thermal was shut off. We didn't want to deal with that. No one wants to turn the thermal system back on 6 months later. Kill it, have it gone, so we don't deal with that, and it's not going to continue as a residual source at the base of the aquifer leading into the groundwater. So there was multiple reasons to go further than we needed to.
Yeah, again, good point.
The guarantee.
Exactly, the guarantee, above and beyond, right? All right, so this is how the site looked. We're standing kind of in the middle of both the electrode well field, and some of the equipment is in the background here. So there's a lot going on in this figure. I'll try to walk folks through it, Scott, and feel free to chime in. So we've got one of the electrodes right here. You can actually see the vapor recovery line coming out of the subsurface. And this infrastructure right here is the electrode wetting system. So it's just dripping water to the subsurface, maintaining contact with making sure the electrode maintains contact with the native material. This wetting system ended up being extremely important to some of the early optimization efforts that I know our team took part in, just optimizing power delivery to the subsurface, which worked out well because in the end, we ended up consuming a little bit less energy than what we had originally designed. So that always feels good in the end. But back to that VR line here, you're looking at part of the manifold going into the steam treatment system over here on the left-hand side. You also have an air stripper over here that is doing some treatment of the condensate that's generated from this steam treatment unit. And then the vapor from that air stripper is tied back into the steam treatment unit. And then in the background, I know you had some issues, Scott, with the owner not being available necessarily for signing of manifest. So we did use a small cell to treat some cuttings, right?
Correct, yeah, because again, a lot of very specific details with this property. We didn't have anyone who could sign off on a hazardous waste manifest. So couldn't dispose of any of our soils, our soil cuttings, our spoils. So we got Genius here, worked with TRS, had a thermal box designed where we drummed up, or instead of drumming up cuttings for later disposal, we put them in this thermal box and treated, I want to say it's about 15 cubic yards, and treated those with thermal conduction. And then when I think that was on for maybe a month and a half, it ran, turned it off, let the soil cool down, sampled it, and it was all below any kind of regulatory threshold, so we could go off as non-hits. It was a very unique solution to what was probably the biggest problem at the site. So it was again very unique, and it was nice to have everything inside. So again, it worked wonderfully.
Yeah. So I mean, there's a whole nother side to this project, right, Brett? This is where you came into play. Scott and Brett, would you mind walking us through what was happening, right outside of the thermal treatment area, that source area, and then what occurred down gradient?
Yeah, absolutely. So thank you very much, Lauren, for the introduction. Yeah, so obviously this is a big puzzle. So just to continue to build on that combined remedy effort, and using some of the synergies from the thermal, we started up in the source area. On this figure, you can see the far northern edge of this plume is where the source is. We initiated with 3DME, our slow release electron donor, an ISCR reagent, and a bioaugmentation, or BDI plus, to continue to eliminate that source and arrest that plume within the source zone where the groundwater contaminants were a little higher. So we implemented that just down gradient of the thermal treatment. Yep, right there, indicated by that blue line. That's right. So, and then as we continue to move down gradient, with the source being handled, with the thermal and cutting the head off the snake, if you will, then the primary goal was to arrest the plume that was migrating off site. And so we utilized our plume stop technology, colloidal activated carbon paired with S micros EVI, and our BDI plus in a series of down gradient PRBs to basically arrest this thing and eliminate that migration towards that barrier, as well as those offsite structures. You can see on this figure here, the logistics was a challenge, just as it was inside the building with everything that TRS had to deal with. Then we move outside, and then we've got the general public we're dealing with on some very busy roadways. So being able to have a very small footprint, and work within those zones in a very busy environment was a challenge. But we were able to get a series of three PRBs that you can see here, one of which you can't see on this figure, but able to implement and get this program working. But getting into this part of it, and this was a very key, crucial part to this project as a whole. Design verification and really understanding the site itself was crucial. As Lauren kind of mentioned earlier, one of the key pieces that we utilized for this, trying to verify a couple things. You know, on the very front end, we had some estimates provided from some historical data prior to Scott and I really getting involved with it, that had a very, very fast groundwater velocity estimate, upwards of 1,500 feet a year. So when we're talking about a PRB, those groundwater velocities are very, very fast, and you know, mass flux plays a huge role in that. And then Lauren also alluded to the repercussions that it could potentially have on hers and the TRS design. So we implemented a technology that Regenesis has developed called flux tracers, and I've actually got one of these little units here. Hopefully people can see this this little thing. But these are in-well devices used to calculate mass flux and hone in on that groundwater velocity. So we deployed a series of these, 5 of them in total, 15-foot long devices throughout this plume to help us really understand basically, you know, how fast is groundwater moving? Is it really moving at 1,400 feet a year? And what kind of mass? Where is it moving? Where is that groundwater contamination actually flowing through our aquifer? In doing that, it really allowed us to fine tune that design and ultimately saving a great deal of money, because we were able to discover that the groundwater was moving significantly slower than our initial estimates, you know, on the order of about 250 to 300 feet a year on average. So, you know, that's a great deal slower, you know, and resulting in roughly $380,000 in savings from a offsite remedial design, being able to shave off both vertical and horizontal extent. And Scott, do you want to share a little bit more on that?
Yeah, no, perfect. Again, this was one of the things we talked with our client too about initially. You know, we really want to get a handle on this, and if we want the results that we're going for, we need to go out there and play scientists for a little bit. So we get up with Brett, got the idea for the flux tracers, got the clearance from the client. We've installed 5 different flux tracers in newly installed monitoring wells, kind of like right down the spine of the plume, from very near the source down to like right along the river. So we had the full length taken care of. Also, while doing that, we collected soil samples to again verify the overall coverage of this clay aquitard that, you know, we knew was down there, but we wanted to put eyes on it. So we were able to tag that at, you know, various depths across the entire project area. It typically varied from, you know, 30 to 34, 35 feet. So, you know, a little bit of undulation in there, but, you know, not to be unexpected. So we were able to put the new wells in, tag the aquitard. So we knew we had the bottom of it, or the bottom of the saturated unit taken care of, put in the flux tracers. And like Brett said, we learned that the contaminated zone was about maybe a third less thick than we thought it was. And we also put a couple flux tracers kind of perpendicular to groundwater flow to get the width of the plume a little more tightly defined. So not only were we able to thin up the injection area, we were able to thin up the width of it, saving, well, obviously about $380,000 just in product, not including, you know, any, you know, driller's time, and like that. So it was very quantifiable. Made the client very happy. Our pilot study costs 35 grand, give or take. But when you can spend 35 and save 380,
Yeah,
very justifiable to a client.
Pretty powerful.
Very good. And then the other thing that it helped us do, like, Brett, or I'm sorry, Lauren mentioned a little earlier, we didn't have to do any kind of hydraulic controls up gradient of the thermal system. We didn't need to slow the groundwater so that the thermal could do its portion. I've heard estimates on, similar size projects in, similar kind of aquifers, about $100,000. We didn't price that out. That's a good back of the napkin. So with this little science experiment, we saved our client close to $500,000 in costs. And again, that makes clients very happy.
A great testimony too that, characterization really never stops. Even during remedy implementation, you continue to, the data density just increases and you learn more and more along the way.
Very important. Yeah.
So
yeah, I'm sorry, Lauren.
No, go ahead.
Yeah,
Dive right into it.
No, just to continue and kind of wrap it up from an overall plume treatment and paint the overall picture, just some statistics here on the sheer size of this thing. We had close to 1,000 linear feet of barrier that went in, 246 injection points. So we had a very large scope of work. But as Scott mentioned, it did vary. You can see here in that table, the summary table there, going down and tagging that aquitard in that bottom zone, was very important. And you can see the depth as it changed as we went towards the river. So being able to dynamically, I guess, roll with the punches, if you will, and figure out where that treatment interval is as we move throughout this injection program was a crucial part. And you can see there the timeline on this was, as we talked about earlier, in the colder months. We weren't able to use the warmth of TRS's building for very long outside, but our guys hammered through, and we were able to have a successful project completed throughout the winter months in Indiana. So it was great.
I remember that last day. We didn't have a very nasty winter at all in Indiana. It got cold a little bit, but it decided to snow about 6 inches on us the last day. We talked about, hey, we want to give the guys a day off, let the snow melt. It'll be 60 tomorrow. And this field crew said, no, we're getting this thing done. So,
yeah, we were
It
pretty
wasn't all
fortunate.
blue skies and green grass, huh, Scott?
As this picture shows, we did look out for the most part. It was a pretty mild winter, and guys weren't too miserable. But to kind of bring home, with that large of an application, a lot goes into that placement validation, if you will, in ensuring where that product is going. We had a lot of products that go in the ground over varying intervals. So really making sure that the distribution was there and achieving that was very important. And it's something that we do throughout the process. So each one of these barriers, we have a placement validation plan. It's tough to see in this figure here, but you can see the injection points laid out there with the individual hoses going to the points. And so we're collecting cores in between our points, making sure that the desired overlap, the radius of influence is being achieved. And this next slide kind of shows that and what that typical placement validation looks like and what we're looking for in that treatment interval. So plume stop and iron, ZVI is it's a great tracer. So we're very fortunate there. You can see in this conformation core that target treatment interval is pretty darn black, and that's exactly what we're trying to target. We're targeting that entire interval and turning it into a purifying filter. So we need a complete saturated zone. And that's what we were able to achieve here and confirm that with our confirmation cores. The figure up there in the top right, that small figure, is a actual groundwater concentration sample. Taking a look at actually the carbon concentration in a temporary piezometer. So we're verifying that overlap and that distribution has been achieved. Yeah, I think that summarizes that one.
Just a quick question, Brett, just walking folks, across this borehole. So you've got that stand that you're looking at here right across until you start you travel into the clay, right? And that's ultimately where you land over here, that confining layer.
Yes, ma'am. Yes, ma'am. Thank you. So that confining layer is there on the right. So we go down and tag into that a bit. And then we pull up and start our injection interval right at the top of that clay. And in this case, come up to about that 16-foot interval right there.
All right, Scott. I mean, all of this work over a really short period of time, did it achieve the results that you were going for when you started to put together this program for your client?
No, I think it's evident, the site maps, they speak for themselves. I mean, one can write a report and read a report all day long, but this picture, it tells you what's happening. We got the uh, quarters prior to any remediation, and I think actually there's even better ones. I think even like further up shows the first quarter of 2024. We still have some detections of TCE, but we have gone from the hundreds of parts per billion into the teens. I think our highest one now is roughly 30, 35 maybe. So we have definitely taken care of the problem. It's proofs in the pudding right there. We're going to continue monitoring for probably a couple more years. I know it's our regulatory environment. They like to do a 1 year of post remediation stability monitoring, and then I'm sorry, post remediation reequilibration, and then typically 4 to 8 quarters of stability monitoring. At this point in the project, we're kind of in a middle of that, because we finished the injections in January, and the most recent sampling was done this January. So, excuse me, would have been the fourth quarter post injection, but the thermal the middle of June. So now we're 2 quarters post thermal shutdown. So we're kind of somewhere in a transitional period where our reequilibration stability monitoring period is started for one, not quite ready for the next, but getting there. Our next thing we're going to do, we check the temperatures out there quite frequently, and I believe we're safe now where we can go back out and reinstall a monitoring well or two in the source area. We didn't need the expense of stainless steel and didn't want to melt PVC. So once we know that the ground in the thermal area is cool enough where our drill can safely work, we'll get that installed, verify that the groundwater where we did the thermal treatment has been taken care of, and then we'll just continue to monitor the down gradient groundwater, like I said, for the next couple of years or so. One little addition, which is not really part of our remedy, but it resulted in some fantastic results. We had subslab depressurization systems on a couple of the buildings very nearest the source area, because we had some fairly high subslab hits, and to be very proactive and protective of the occupants of those buildings, we had installed SSDS systems, sampled them during the winter summer worst case kind of weather scenarios. Past couple of years, we have passed that. We have no indoor air exceedances, so we're now kind of in a let's check it again in 5 years.
Yeah.
We'll keep the systems operational just as a precaution. Another thing we do on a monthly basis, just in an abundance of caution, is we do methane monitoring in and around all the monitoring wells we've got installed, because of the potential for methane in post injection. We all know can be a potentially explosive problem. We don't have it. There is high methane in a lot of the wells, which we would want to see for the dechlorination. But in the areas where we're near buildings, we don't have that, more than likely because the injections weren't near buildings. They were in rights of way. So where we're getting the excessive methane concentrations, it's not near any occupied structure, and the wells that are near those buildings all come back clean. So we're looking at this in many avenues. Our ultimate goal is to protect human health and the environment. We don't want to, create a situation while solving the problem that puts people in danger. So I guess all in all, everything we've set out to do for this project has been accomplished so far. Clients could not be happier, and they're just they're waiting to have a party when we're all done.
Great summary of the project and where it's at, and some of the logistics that do go into, having a couple of different technologies implemented at the site, with a combined remedy in place. There are, monitoring programs that are tied to those technologies, right? So you are managing a couple of different monitoring programs right now to bring it across the finish line.
Mm-hmm.
So we're going to open it up to some questions. I see in the Q&A chat space that we've got a lot that are building up. I know some were answered along the way, and there were some comments that were given. Appreciate the engagement here today, but I see a question. This is a quick one from James Griffin. James is wondering, Scott, is this a private project, or is this something that has funding from a public entity? Would you mind commenting a little bit, if you can, about your client here?
Yeah, it's fully a privately funded project. A lot of the funding comes from insurers for the former owners and operators at the facility, but it is completely overseen by, our version of the EPA, the Indiana Department of Environmental Management. So everything we do, we sample, write our report, send the results, have good interaction, with the state regulator, with our project manager, Syed. Everything is going there. So while it's a private project, it's publicly available information on what we've done.
And James actually has a follow-up question. Did you interact with just a single entity, or were there several parties that were funding this remedy?
There was several that we had to make all of our taskmasters happy, and they were all very pleased. From the beginning of the project, when we, kind of conceptually came up with, hey, what if we cook it and inject it? They're like, that could work. How would it work? And so it was a very open dialogue between us and them. What are your goals? What do you want us to do? How clean is clean enough for you? They're like, we want closure. We want this problem to go away. And again, we do a lot of work with insurance companies, and usually their biggest question is, when will we be? Like to close sites, they like to close their files. Accomplish both by, doing what we did here, work a site, work the problem, clean it up. They can put it to bed, and our client gets an over their action letter.
Yeah.
That's where we're hired to work ourselves out of a job. Close it right.
It's a good way of describing
Right
it.
way to put it.
Sorry about that.
That's the job.
Ruth Kennington has a question about, you mentioned the regulators, IDEM, as I refer to them as, but the state of Indiana. IDEM was involved in this project. Could you explain a bit more about some concerns that they had along the way about the remedy, or what level of involvement did IDEM have?
Well, initially the project was brought to us because it had seemed to stagnate, and the IDEM wasn't getting the push to get it done as quickly as they would have liked it to be done. So that's when the carriers came to us and said, we might need a fresh set of eyes. And then took it over. Again, multiple meetings with IDEM downtown at their offices, I think once or twice, and then the world broke when COVID hit. And we had to, do a lot of this with people and just bouncing ideas off of each other, virtually, and involved IDEM from the get-go. They loved the plan and said, "Wonderful, let's go do it." And then even towards the end of the project, I want to say it was probably somewhere early June last year. The project manager wanted to bring out his project team, his geologist, his risk assessor, chemist, to view the site. They wanted the nickel tour of a thermal system, because honestly, it's a very common technology, but it's not as common as others. A lot of people had never seen one before, so they wanted to see it. They had a younger staff who never seen it before either. So we're like, yes, please, we would love to give you a tour. So we spent probably 2 or 3 hours walking through the equipment with your guys on site. Steve was fantastic, like always. Just kind of just giving them like a private tour of the thermal, how it worked, what we did, everything like that. Then we walked around, showed them where the injection lines were that we put in with Regenesis. But a couple hours with boots on the ground with the regulators, and couldn't be happier. So if you can work with them or you can butt heads, and I find it to be much easier to work with the regulators, because at the end of the day, you want the NFA letter. They're the ones that issue those. So
no further actions important in the end, right? You want
so,
all of this to mean something.
right. So if they have a request, you meet it, typically. So again,
Yeah.
it was great. It was a great chance for us to earn their trust, answer their questions, and educate the younger regulatory staff. So it was a win-win.
Yeah, and the logistics to get them out to the site is fairly easy at the site. You have to admit, being right down the street from items, Indianapolis location makes this site certainly easily accessible for them. We realized, not all sites are that easy, but having them out was an easy thing for us to host. So
Okay.
I've got a couple questions for Brett here that are piling up. Brett, Dennis Nag wants to know if you subcontracted out or self-performed the injections for the PRBs, the passive reactive barrier walls.
Yeah, so that's a great question. And it's a little of both, I'll say. So Regenesis doesn't own geoprobes. So we do subcontract out the drilling component, but Regenesis does handle all of the mixing, the actual distribution monitoring, all the report preparation from the amendment application. So it is a combined effort there, but we do subcontract a local direct push contractor generally when we show up at a site.
Yeah. And then another question from an anonymous attendee, and no judgment over here. You don't have to make yourself anonymous, but a great question from them nonetheless. They're wanting to learn a little bit more about the flux tracers that you referenced. Are these tracers that remain in a well, and obviously they generate a lot of useful data for the groundwater, but can you leave them behind? What's the logistics that goes into them? And if it's a well that you put them in, what's the minimum diameter well that's required for it?
Sure. So yes, the devices, they're a stainless steel canister, and they are built to spec for each individual well. So we work with Scott to identify the 5 wells that we wanted to use. Scott provides us the screened interval, and that's what we're trying to target, the overall depth of the well. And we take all of that into consideration, and they're built in our laboratory for each individual well. They are currently only built for 2-inch wells, traditional 2-inch monitoring wells. And the tolerances are pretty tight. So that's where they're currently at. And typically they are deployed for 2 weeks. So we ship them directly to the client for deployment. They come in a standard igloo cooler. Scott can attest they're pretty straightforward to deploy, take about 10 minutes a well. You literally lower it down in the well, let it sit for 2 weeks, remove it from the well, repack it in that cooler, and then it's returned to the Regenesis laboratory for analysis. And then we prepare a report on the findings and submit that back to the client. Now, that 2-week timeline is typical. If we have a really fast moving aquifer or a really slow moving aquifer, it can be adjusted as needed, but typically it's 2 weeks.
And Brett, a follow-up question. Oh, I'm sorry, Scott, go for it.
I was thinking just one word for those who are going to use them. Again, they're fantastic. They're heavy. Because they're, again, they're stainless steel, and then you're pulling them up and they're saturated. We had 5 of these in the long train.
Yeah.
15 foot of them can be a challenge.
Gotta use those guns.
It took a
That's
couple of
right.
us to pull them up, leather gloves. I think we even deployed a couple of vice
Winch.
grips to really clamp onto the cable and pull it up. So it's
Yeah.
depending on the length
15
of
foot
it.
sections are the largest that we deploy. We can deploy them as little, 5-foot sections. Those are much more manageable. One person can handle that without a problem. But yeah, 15 feet of saturated carbon gets a little heavier.
Just a little bit.
Yeah, great advice for folks considering their use. A follow-up question from Bill Butler is about the contaminants of concern that you're looking at when deploying those flux tracers. Could you comment about, what you can chase? Is it just VOCs? Can you do SVOCs or maybe even some metals? Fair to comment on that?
Sure. So currently we do chlorinated solvents and PFAS for these devices. Now we do have offerings and options for petroleum components, but it's done a little bit different. But the flux tracer devices currently are for chlorinated solvents as well as PFAS.
Yeah, thank you. And then we've got a series of questions that are in our Q&A right now. I am afraid that we have gone a little bit over on time. We do try to keep these things to about 45 minutes. But I want to end with one final question because it's always asked at any one of these projects. And Scott, this one's for you. It's a tough one. I'm putting you on the spot here, but can you share the overall cost of, the ERH and injection strategies on this project?
That's
it's always asked.
so yeah, that's probably a confidential answer.
Well, let me turn to the contact information on the screen. If you want to learn more, maybe a private conversation is in order.
Yeah, it was. What I will say is between the 2 combined remedies, we were at 7 figures.
Yeah.
So
I know we didn't get to everyone's questions today. We will compile the list and we will answer them in writing and send out a list of questions and answers to all of the attendees. So I really appreciate all the engagement today. Despite not having Gorm here, we so appreciate it. And we look forward to responding to each and every one of your questions in writing. So we will be in touch and join us for the next webinar series once it's scheduled on the horizon. I think we're looking at something about 4 to 6 weeks from now. So I look forward to sending the invitation soon. Thank you so much to our panelists, Brett and Scott, today. Appreciate your time preparing for this and sharing this project.
Listen, just one final thing. Brett, Lauren, and I will all be at Patel this year in June. Regenesis is putting on a talk about this project very specifically. So if you're out there, wonderful. Be nice to meet you guys in person. Swing by for a little bit and shake our hand.
Absolutely. Thanks, Scott.
You're welcome. Take care.
All right. Bye, everyone.
Thank you, Lauren.
Thank you, guys.
Scott, thank you.